All right, ladies and gentlemen, today we're going to talk about sound waves, and this is going to be the whole chapter 12. So sit down, relax, and we're going to start. So this is going to be important for sound waves. Remember, sound waves are transverse waves. So when we talk about this, there's two things that trans waves do, and that's rarefication and compression. Rarefication is the process of that waves are thinned away. So when we're having waves in the air, sound waves, our vocal cords compress and then relax at various different frequencies and intensities, depending upon how loud we want to be, how soft, and so forth. For some that comes from the lungs, projecting out. But all of this sound is basically when we take something and we have a compression. Then we have what we call rarefaction, then gets compressed, and refraction, compressed, refraction, and these are sound waves. And this is what we hear when this sound waves hits our eardrums, and that vibrates the three little bones that's connected to the eardrum. So here are the two things. Now I'm just going to go through these definitions fairly quickly. We have pitch, which is a band of frequencies, and this is what we usually hear. Is this pitch of about range of 10, 15 hertz of frequencies that come into our ears. Very rarely can we identify the difference between a 350 and 351. It's basically a blend of those wavelengths. The speed of sound actually depends on the media or the medium, the material that the sound is going through, and the temperature of that sound. And the sound is emitted in all directions. So when we talk about, that means people behind me can actually listen to me and hear me. And it's coming out, it's projected out in, let's say, an arc. Sometimes we have a point source, that's when we have a circle. And then we have something called the Doppler Effect, where the wavelength depends on the moving objects. If the object's coming to you making a noise, the wavelength gets shorter, the frequency gets higher, and as it leaves, it's the opposite way. The wavelength gets longer, and so the frequency gets shorter. So these are some of the things that we hit in the reading, and you guys need to start read that book for more information. So in density, this is what we're going to be working on more for the problem set, is the change of energy through a plane as a function of time. So eardrum, piano, whatever, you have a board, say our eardrum. Sound's coming in this way, it's vibrating. This drum's vibrating as well, and it's transferring that vibration, contraction, rarefication to a series of bones that actually vibrate at different frequencies, and then transmits that frequency through to the ear. So a change of energy as a function of time. More compressed it is, more energy. And so what we have is density is equal to power divided by area. And since the sound wave is considered a sphere, we're looking at the surface area, which is 4 pi r squared, and here's the equation at this point. So density is equal to power divided by 4 pi r squared. Now, as I want to point out, as the distance increases, and we use r for the radius, it's going to be the distance from where the sound is made, the source, to the person out here. As we go farther along, it becomes more of a plane-like. And that's natural. So this is what we do with intensity. We'll be calculating intensity is based on distance. Now, if we're talking about us hearing, the biological function of hearing, the audible sound is dependent on intensity and frequency. You got a nice graph in the textbook about this. Now, I want to point out that the human ear is very sensitive to sound. So it's sensitive that the change in pressure in the sound wave, that when we vibrate, is 3 times 10 to the minus 10 atmosphere. That is extremely, extremely small. So we're very sensitive to very small changes of pressure. And that's how we can hear. So all of this is all based on our eardrums. Now, we can actually force a vibration onto another object. You can Drums do this, guitars do this. You have a string that is vibrating. So here's the string. It's underneath the guitar. It's held at both points, and there's a little bridge. And this thing vibrates, and it transmits that vibration down into the body cavity. Remember, guitar is hollow. It's going to take that sound. It's going to vibrate as well. The air is going to vibrate, and which transfers the vibration in the air, and then it's going to gain more intensity. It comes out, and now we have music. So this is what we have, and you can actually, again, you can have you have something vibrating. You bring it close to something else that can vibrate. It can vibrate as well, force vibration. Now resonance is you have an applied force, wind, of the vibration is identical to a natural frequency of a system. You can get that, you can increase the amplitude of the system. And the funny thing is, bridges are susceptible to this. And you can actually look at this YouTube video of the bridge over the Tacoma Straits in Washington State, and you can see the wind picking up, the bridge starts swaying and vibrating, and next thing you know, it collapses. No human injuries were involved, luckily. There was one fatality of a small puppy, unfortunately, but they have a nice video of this. It was right before they opened the bridge to traffic. So we're going to go on to harmonics, and harmonics has to deal with standing waves. So when we look at standing waves, we're talking about a string that is attached at two ends, and it's going to vibrate. And it's going to vibrate back and forth. It's going up, and then the reciprocal is going back. And if you got a lot of these vibrations occurring, you're going to see that's basically looking at it from perpendicular to it. It's going to go up and down. You're going to see the line at both times. It's going that fast. Well, the fact is, with these strings, it's attached at both ends. This is going to be important because this is where we have two nodes. And for this demonstration drawing, this is the antinode. And what's going to happen is that this is what we call the fundamental frequency. Because you can't the wavelength is basically stuck at the length of this string. We're going to pluck it, and it's going to vibrate. It may not, this is kind of exaggeration of the distance, but it's going to vibrate a little bit, and this is going to be the fundamental frequency. So the fundamental frequency is when f is equal to the speed of the string divided by 2L. So v is the speed of the string. So we're looking at the string only. And so the fundamental frequency is going to be v over 2L. So if we look at so frequency times wavelength is equal to speed. So 2L is the wavelength. And how is that? So here's our string again. If there's a node and here's another node, so we've got two nodes and one antinode, this is actually 1/2 of the wavelength. See, the wavelength actually goes up and then down and back up. So this portion, whoops, to here, or from this node to this node is going to be one wavelength. And this is going to be important. So can it be higher than 2 length? No, because that means we're going to end up with an antinode somewhere around here or different part of the frequency. And it can't happen because we have to have a node at each end. So with our fundamental frequency, the wavelength is 1/2. The wavelength is 1/2, is twice the length. Second fundamental frequency, the wavelength is exactly the length of this, up and down. This is our second fundamental. 3 nodes, 2 antinodes, 1 wavelength. So again, draw this. Here's our string. This is the length. If we had the first first fundamental frequency is going up and heading towards down, but it doesn't fulfill that second part. So this is actually 1.5. So the wavelength is double this, 2L. Now the second fundamental frequency, here's the string, L, up and down is coming back up, 2 nodes, 3 nodes, 2 antinodes. This is one wavelength. So the wavelength is actually equal to L. And so on so forth, we're going to decrease the length of the wavelength by 1/2 of the length. Third frequency is going to be 3/2 L. Then the next fourth frequency is going to be 1/4 L, so on and so forth. So you get the idea of how this is going to work. Excuse me, 4/2 twice. No. I forgot the calculation. Fourth, the length is going to be 1/4. I know it. It's going to be a long day, guys. Let's go to harmonics. So this is what we're talking about. And this is called the third harmonic frequency, the fourth harmonic frequency. So this is again, this is speed of string. This is the order of harmonic. This is the length of the string. And this is my frequency. If at N, it's the the fundamental harmonic. Then we go to second, third, fourth, fifth order, so on and so forth. Now, as we're going through this, let's see how a pipe order works. And we're going to look at an open tube. And at the end of each tube, this is an open tube, the antinode is present. This is different from a string. Now, when we talk about an open tube, here's my open tube. When sound is released, comes out of the tube, it has to be at an antinode, either the maximum or minimum of the wavelength. So it's going to come down like this. Here's my node, 1 node, 2 antinodes. And this is basically one wavelength. So if this is 1/2 of a wavelength, so we go to our second fundamental, it's going to be one wavelength. So we go down, up, down. So 1 antinode, 2, 3 antinodes, here's my tube. Here's my first node, here's my second node. And for music to come out of an open tube, the antinodes have to be at each end by design. And we're talking about open tube, a flute, organs, stuff like that. And this is what I call a harmonic series with an open pipe, where V is the speed of the sound in the pipe. This is in air, or whatever gas we have. It's now in this. It's not a string now. It's not the pipe material. It's actually the sound vibrating inside the pipe, and everything. And this is the length of the pipe. Again, this is harmonic series with an open pipe. Here's the difference is the speed, what this velocity means, and the length. The calculations are very similar. Now, with this harmonic series with a closed pipe, it's going to be a little bit different, because I'm going to show you that here, because one end's closed. So what happens is this is a node, and to get the sound out, it has to be at an antinode. Here's my antinode. So if this is my wavelength, and I'm just looking at this is 1/4 of my frequency, 1/4 of my wavelength. So we are now dividing this by 4. So for a closed pipe, we are now having the wavelength, the fundamental frequency 1, is actually 4 times the length of the pipe. Same parameters of the last question, but we're now looking at this number being 4 instead of 2, basically because of how the closed pipe emits sound. Node is at the closed end, antinode at the other. And this is how pipes work. All right, quickly, timbre is the quality of sound. This is chart on 428 if you want to take a look at it. More things are in harmony, the better quality of sound. You guys all know this. And now, something we call a beat. We're going to lab on this. 2 ways to structurally interfere, loud, soft, loud, soft. And if you count the softs, you can figure out how many beats per second are the difference in frequencies. This is used years ago when radar operators and stuff like that were trying to figure out how to interfere with sound. And they could figure out the frequencies based on the different beats they can count. And so this is a way we can, if we have a transmission of an unknown sound, we can figure out if we interfere with a different frequency, if we get it to where we just hear a beat, elimination of sound in the noise, we can figure out the frequency. And that is it. Bit of a long lecture today. Have a nice day, folks, and we'll have another one of these